Hi, I'm Jay, and if you browse popular science media, you'll hear about curvature, forces, and so many other things in reference to what people think of as gravity. We won't tell you what gravity is, per se, because science is models of reality, not necessarily reality itself. However, we will describe its effects in a more scientific manner than pop culture has led you to believe. First, I'll let Austin take the wheel and explain what Einstein called the equivalence principle.
Imagine you're in a box. There is a flashlight attached to one side of the box that points to the opposite wall. If we turn on the flashlight, we expect the beam to cross directly to the other side. However, this does not happen. What we see instead is the light beam curves down and hits the ground. How could this be? Should light not travel in a straight line? If we instead imagine we are outside the box, and in fact the box was accelerating upwards, it would become clear that the light beam had in fact been traveling in a straight line all along. The apparent curving of the light we had seen inside the box was simply the floor moving upwards to meet the light beam. What is interesting about this thought experiment is that it yields the same result for any general free body. A ball that is thrown across the box will appear to follow a parabolic trajectory in the frame of the box. This is significant, as this behavior is exactly what one would expect when tossing a ball on the Earth's surface. In fact, it is impossible to determine if you are standing in a box accelerating upward at a constant rate, or if you are standing in a constant gravitational field. This idea is called the equivalence principle, equating an accelerating frame of reference to a homogeneous gravitational field. It is for this reason that, despite Newton's theory of gravity predicting only massive objects to attract other massive objects, we may speculate that the trajectories of massless particles such as light should also bend in the presence of gravity. In fact, this line of thinking is what led Einstein to his theory of general relativity, which predicts the bending of light in the presence of massive objects.
One such massive object is a black hole, where at what's called the event horizon, even light cannot escape fast enough. In these simulations, we see light rays starting at very similar points become spread out, taken in by the black hole, never to be seen again. Light can be thought of as being lensed around the black hole because of what we call the equivalence principle. According to Einstein's theory of general relativity, light does in fact follow a straight line. It's just that, from our perspective, it seems to curve. The same way that it looks like planes fly in direct paths to their destinations, but really it's because of the 2D curvature of the Earth's surface, which is a great analog to the 4D, both time and space, or space-time, curves due to massive objects. Space-time is not an easy thing to understand, and it's even harder to do the math for. So if you made it this far and understood some of the key concepts, you're already well on your way to be a physicist. If you stick with it, that is. So thank you so much for taking the time of day to watch this short video. Bye from me and Austin.